Hey guys, hi, welcome back. So in the previous video, we have discussed about the Maxwell's potential and the Maxwell's equations. In this video, we shall discuss about the Clausius Clapeyron equation, and we will derive the Clausius Clapeyron equation using the Maxwell's second equation. So first, let's see what is the Clausius Clapeyron equation says us. Okay, this equation is something which shows the variation of the melting and the boiling point with pressure. What does it show? Using the Clausius Clapeyron equation, we can see the variation of melting point and boiling point with pressure. When pressure is changed, then we will see a variation in the boiling and melting point, right? And you see this law, it is obtained on the application of second law of thermodynamics. It is an application of the second law of thermodynamics. And remember that the Clausius Clapeyron equation, it is said to be the first latent heat equation. It is said to be as what? It is said to be as the first latent heat equation. All right, and using this Clausius Clapeyron equation, you can find the effect of melting point and boiling point of substance. All right, during phase change, we can study the effect of pressure on melting and boiling point. All right, now we will see the formula. This is the derivation of the Clausius Clapeyron equation using the Maxwell's second equation. Okay, so we have already done the Maxwell's second equation. It is del S del V at constant temperature equals to del P del T at constant volume. So now when you will multiply T on both the sides, in the left hand side and also in the right hand side, then you can write it as what? T del S del V, all right, at constant temperature equals to T del P del T at constant volume. Now you see this T del S, this term, this T del S, it can be written as del Q using the second law of thermodynamics, right? Yes or no? T del S can be written as del Q using the second law of thermodynamics. So this is what you have to do. You can write here del Q by del V at constant temperature equals to T del P del T at constant volume. All right. Now you see here you are having what? This is del Q. So this del Q will be equals to what? L. And there is what? And here you are having del Q by del V. This term will be as it is. This term is something that is going to change. Del Q will be L, that is the latent heat, and del V, it is the change in the volume. If I consider the final volume to be V2 and the initial volume to be V1 for a substance, then I will write del V to be what? V2 minus V1. And L is the latent heat. We have already said that the latent heat is the amount of heat required to change the phase of 1 gram of a substance, keeping the temperature constant. So we have said in the last video, so this is what? This is the latent constant. That means if a body changes its state and temperature, absorbing latent heat, all right, a body is changing its phase and temperature, absorbing latent heat, having specific volume V1 and V2 in two phases. So this is the latent heat L. Phase change is there from V2 to V1, sorry, V1 to V2. So the final is what? V2, the initial is V1. So it is L by V2 minus V1, and it is equals to T del P del T V. Clear? So from here you can write del P del T, it is equals to what? L by T V2 minus V1. And this equation, which we have derived from the second Maxwell's equation, it is said to be the Clausius Clapeyron equation. And using this equation, we can see the effect of pressure on the melting and boiling point when there is phase change. So now we will see the effect. Clear, this formula is very important. You will get number of questions, multiple of number of questions in all the examination. Either it's GATE, either it's JEST, or you can say IIT, JAM, CSI, and NET. All right. So now let's come to the application. Application of Clausius Clapeyron equation. First, we will see the effect of pressure on melting point of solid. On melting point of solid, we will see the effect of what? Pressure on melting point of solid. So first we will see the general case. Generally what happens when solid is changing into what? Liquid. Suppose I'm considering the volume of solid to be V1 and volume of liquid to be V2. Generally what happens? The volume increases because when solid is changing its phase to liquid, the volume increases as for wax or sulfur, like that example you can consider. So when V2 will be greater than V1, then V2 minus V1 is what? Positive. If V2 minus V1 is positive, we have seen what? dp by dt, it is equals to what? It was equals to L divided by T V2 minus V1, right? If you see here, if this V2 minus V1 is positive, then this dp dt, it is what? Positive. That means the melting point, it is directly proportional to pressure. Means if dp dt, if del p is increasing, dt is also increasing, right? And that means melting point will increase when the pressure is increased. Melting point will decrease when the pressure will decrease. This is the general case. But sometimes if you consider ice, in case of ice, what happens? When solid is converted into liquid, ice is converted into liquid, in that case, the volume is what? Decreasing, right? Means if solid is converted, if ice is converted, if I consider this to be ice and if I consider this to be water, in case of ice and water, what happens? The volume decreases. That means V2 is less than V1. In that case, V2 minus V1 is negative. If V2 minus V1 is negative, then this particular dp by dt, it is a negative quantity. That means in this case, in this is an exception case, in those cases, what happens? The melting point, it is inversely proportional to what? Pressure. The melting point is inversely proportional to pressure, means when melting point will increase, pressure will decrease, and when pressure will increase, the melting point will decrease, right? So this is something you have to remember. This is the effect of pressure on the melting point of solids. Next, you see the effect of pressure on boiling point of liquid. That was the effect of pressure on melting point of solid. This is the effect of pressure on boiling point of liquid. This time we will see for the boiling point of liquid. Now you see when liquid is converted into what? Gas. In that case, what happens? Obviously, the volume is what? Increasing. So V1 is the initial volume of the liquid, and V2 it is the volume of the gas. So you see here V2 minus V1, it is positive. If V2 minus V1 is positive, then dp by dt, it is also positive. That means the boiling point, it is directly proportional to the pressure. Means if this dp will increase, dt will increase, and if dp will decrease, dt will decrease, right? That is the boiling point of liquid rise with increase in pressure and vice versa. Or you can say the liquid will boil at lower temperature under reduced if the pressure is reduced, then the liquid will boil at what? Lower temperature, and if the pressure is increased, the liquid will boil at higher temperature. Clear? So these are the very important points related to the Clausius Clapeyron equation. So it is not a very complicated topic, very easy. So these are the things that you need to remember. Clear? And I would like to say the one thing, you can find the derivation of Clausius Clapeyron equation using many other processes also, but I have used here the second Maxwell's equation to find it out. All right. Now let's see the questions. Okay, here it is said the boiling point of a liquid at pressure P0 is T0. Its molar latent heat of vaporization is L, and the molar volume of liquid, it is negligible compared to the vapor phase. So the vapor phase obeys the perfect gas equation. The boiling point at pressure P is given by, here it is said, the boiling point at pressure P0 is T0. This is the initial pressure, initial temperature. Molar latent heat of vaporization is L, and molar volume of liquid, it is negligible compared to the vapor phase. Now you see the vapor phase, it is obeying the perfect gas equation. You have to find the boiling point at pressure P. So first it is said V vapor, it is very, very greater than what? V liquid, because it is negligible. That means V vapor I am considering to be V2. It is very, very greater than V liquid I am considering to be V1. Now the Clausius Calpeyron equation was what? dp by dt, it is equals to L by T V2 minus V1. So here I can write it as dp by dt, it is equals to L by TV2, because V1 is negligible. Now you see the vapor phase, it is obeying the perfect gas equation. So if it is obeying the perfect gas equation, then I can write PV2 is equals to what? RT, right? So from here you can write V2 is equals to what? RT by P. Clear? And now if you substitute here this particular thing, now first of all you see here, left hand side is as it is, in the right hand side it is L by what? T. It is 1 by V2. So you will write it as what? P by RT. Now you see, if I bring P to the left hand side, then it is dP by P equals to L by R. It is constant term. I'm keeping it outside because we will integrate it. And here you can write it as what? You can write it as dt by T square, right? Now you see, if you integrate this entire term, the limit will be what? The initial pressure was P0, the final is P. The initial temperature is T0, final is T. Now when you will integrate, you see, you will get what? Ln T. So when you will put the upper limit and lower limit, you will have P by P naught. In the right hand side, L by R is constant. Integration of 1 by T square will be what? Minus 1 by T. So it's negative. So I'm putting the lower limit first. So you will write here what? 1 by T naught minus 1 by T. Now you see this 1 by T naught I'm taking common so that the answer matches the form of the options. So I'm writing ln P by P naught, it is equals to what? L by R T naught. So it will be 1 minus T naught by T. All right. If you compare, then you will see option B is the correct option. Ln P by P naught is equals to L by R T naught into with 1 minus T naught by T. So you have just considered the condition given to you. You have used the Clausius Clapeyron equation and the ideal gas. So this is how you can find. Now let's see the next question. Here it is say the condition for the liquid and vapor phases of a fluid to be in equilibrium. It is given by this equation. This equation is giving the condition for the liquid and vapor phase of a fluid when it is in equilibrium, to be in equilibrium. Now you see if the vapor phase is obeying the ideal gas law, which is correct. We have to choose one graph which is correct if the vapor gas is obeying the ideal gas law. Now first of all, let's write the ideal gas law. Ideal gas law. If I write P V vapor, it is equals to what? RT. This I'm writing for N is equals to 1. From here you can calculate that V vapor will be equals to what? RT by P. This is the same thing that we have done in the last question. All right. In the same way we will proceed. So from here what you will get, V vapor is equals to RT by V and you are given dP by dt. It is equals to QT by T V vapor. Now, if I substitute here V vapor's value, then you can write it as what? QT by T into with what? You can write it as P by RT. All right. So from here, what you can write? You can write dP by P. It is equals to QT by R, and here you can write dt by T square. Now, if you integrate both the side, and I am taking here also the initial pressure to be P naught, final to be P, initial temperature to be T naught, final to be T. So from here, if you see, when you will integrate in the left hand side, you will have what? Ln P by P naught equals to, in the right hand side, you will have QT by R, and within the bracket, you will get minus 1 by T. So I'm writing the lower limit first, 1 by T naught minus 1 by T. So you can write here ln P, it will be equals to what? Ln P naught plus QT by R T naught minus QT by RT. Now you see here, if you consider this term, because the graph is between ln P and T, so you have to see this term. So if you see this term, if T is tending towards 0, then if denominator is 0, then you know no, it will be what? Infinity. Yes or no? Then what will happen? Ln P will be what? Tending to infinity. Right. But here one negative sign is there that you have to see. Next you see when T is tending to infinity. If T is infinity, if anything in the denominator you have infinity, then what will happen? It will be 0. In that case, you will have only this term, and this term is what? It is a constant term. That means then ln P will be what? It will be a constant. Now you see the first condition. If T tends to 0, then ln P is what? Infinity and negative of infinity. If it's negative of infinity, the option B is wrong. Correct. And the other options you can see. Next you see if T tends to infinity, then ln P is what? Constant. Constant means what? After a certain time, first it will be what? Infinity, and then it will be having it will have a constant graph. If you see, the first graph is not that. All right. The second graph is already out. It is eliminated because it is in the positive side. So the third option, if you see, the third option is the correct option, because you see here when T tends to 0, then this ln P now, it is negative of infinity, and when T tends to infinity, then ln P is a constant. This graph is showing this particular conditions, right? So the correct option is option C here. So this is how you can calculate. Now next, one more topic I have added here. That topic, I think you'll get very few questions, and I'm not going to the very deep derivations and explanations of this one. We will just see the basic things here. That is, the topic is diffusion equation. Okay, so I have written the diffusion equation in 3 dimension, 2 dimension, 1 dimension, and this is for Brownian particles. All right, now you see here for 3 dimension, if you see here, rho RT, it is equals to n prime by 4 pi dt whole to the power 3 by 2 e to the power minus r square by 4 dt. Here similarly for 2 dimension you will have n prime by 4 pi dt to the power 1, and this term is as it is. In case of 1 dimension it will be 1 by 2, rest everything is same. Means you have to see 4 pi dt, this terms power, and you have to remember that it is d by 2. For 3 dimension it is 3 by 2, d is denoting the dimension. For 2 dimension is 2 by 2, so it's 1. For 1 dimension it will be 1 by 2. Here you see this d na, it is the displacement coefficient. Now using this diffusion equation, sometimes you will be asked to find the mean square displacement. So the mean square displacement in the 1 dimension it is what? 2 dt. In 2 dimension it's 4 dt, and in 3 dimension it is what? In 3 dimension it is 6 dt. So this is very important. You will get questions in GATE and sometimes in CSR net also. So these things I think you need to know so that you can solve the questions. And these diffusion equations, these are for Brownian particles. These are for what? Brownian particles. And you remember that Brownian motion is what? When atoms and molecules, just I'm saying, giving you an idea, when atoms and molecules, they will move randomly, then they will collide with each other, right? And they, because they have kinetic energy, then they will have kinetic energy. Then you see random moving atoms or molecules, they will randomly collide, and with larger particles they will collide, and the displacement is given by this one. The displacement of one particle is there, and we are taking the mean displacement of all those large particles. So this is denoting the mean displacement of all those particles. All right, so this is for 1 dimension, this is for 2 dimension, this is for 3 dimension. I will solve 2 questions so that you can get an idea what type of questions you can have in the examination. This is just for an idea, okay? So I'm not gone to the very details of the explanations. Now let's see the question. So the first question is, a large number of n Brownian particles in 1 dimension start their diffusive motion from the origin at time t equals to 0. The diffusion coefficient is d. The number of particles crossing a point at a distance L from the origin per unit time depends on L and time Ts. It is said a large number of n Brownian particles are there in one dimension, and they are starting their diffusive motion from the origin at time what? T equals to 0. Diffusion coefficient here it is d. The number of particles crossing a point at a distance L from the origin per unit time is per unit time. The number of particles which are crossing a distance L from the origin, it will depend on L and T as what? That number of particles crossing this particular area will depend on L and T as what, that you have to find. So first of all, we will write the equation of Brownian motion. Equation of in case of 1 dimension, what happens? In case of 1 dimension, A is equals to what? A, the constant. This constant term is what? It is n by 4 pi d t whole to the power 1 by 2. All right. This is this. Clear. Now here you are having what? This is rho rt. You are having rho xt. It is 1 dimension. I'm considering it to be x. This is to be t. So it will be equals to what? N 4 pi dt whole to the power, I'm considering 1 by 2. Here you will have what? E to the power minus r square. Here it will be L because the distance is L here, divided by 4dt. Right? So if you see here, this is what? Rho xt is equals to n by 4 pi dt whole to the power 1 by 2, that is root over e to the power minus L square by 4 dt. So you can see the correct option here is option A. You have to just write the formula. This was just asking you for the formula in 1 dimension. right? So this is the answer. So this, you might get directly the question, that you don't get confused with the question. Just see how it is asked about the one dimension. In two dimension also you will have like that, only in three dimension also you will have in the same way. Now you see, directly you will get the equations. Otherwise you will be asked to find the mean square displacement or the any question related to the mean square displacement. So the second question is related to the mean square displacement. So now let's see what it is. Consider two independent diffusing non-interacting particles. You have to consider two independent diffusing non-interacting particles in three-dimensional space, both placed at the origin at time t equals to 0, right? You're having two independent diffusing non-interacting particles in three dimension. R1 t minus what? R2 t, right? This is the displacement of the first particle. This is the displacement of the second particle at time t. Clear? Now you see, if you write here, for the first particle, the mean square displacement will be how much? 6d1t. For the second particle, the mean square displacement will be how much? 6d2t. Yes or no? It will be 6d1t and 6d2t. Here one square will be there, okay? The square is missing. There is a square. So now you see, this entire term, if you evaluate, you can write it as what? R1 t, R1 square t, yes or no? Plus here you can write what? You can write it as R2 square t, and here it will be what? Minus twice of what? R1 t and R2 t. This is just the formula of a minus b whole square. Now when you will do so, here you have to put the average value symbol, okay? Don't forget to give that. Clear? Now you see here, if you write here this R1 square t, this is how much? It is 6d1t plus this will be how much? This will be 6d2t. And you have to remember that R1t, the average value of this is 0. At time t equals to 0, these values will be what? 0. Alright? The displacement is 0. So you can write finally the value of this quantity. It will behave as what? 6 will be common and t will be common. And it will be what? d1 plus d2. Alright? So it will be what? 6 t d1 plus d2. That is the correct option, is option A. The question was quite simple. Two independent diffusing non-interacting particles are there in three dimension. Both are